Thanks, Zoe, for the introduction. It's a joint work with Bruno and Tom. Tom is here. Okay, so let's begin with type inference. So I believe all of you know type inference. It makes programming easier. You don't need to specify the input types and output types all the time. Well, Hindley-Milner type inference is one of the most famous one. It's a perfect algorithm for rank 1. But if we want higher order types, for example, this h-poly function, the parameter type is a polymorphic type, right? And it cannot be handled by Hindley-Milner type inference. Type inference for higher ranked type is useful in practice, but unfortunately it's proven to be undecidable if you want full type inference. So we need to make compromises, for example, type inference, partial type inference, or annotations in the case, right? And bidirectional type inference is also very popular these days. Dunfield and Kwarshanswamy in 2013 proposed complete and easy bidirectional type checking for higher ranked polymorphism, so he has all the ingredients we want. Their algorithm is easy, which is an elegant predictive algorithm. I'll explain that term later. They support annotations, and they prove that their algorithm is sound and complete with respect to their specification. But unfortunately, it's a 70-page long manual proof, and I don't want to read that, actually. And we found several flaws, actually. So we want formal verifications. And it's usually a difficult task, but we did it. We provide a new algorithm with a mechanical formalization in a Bella. So basically, we are the first to do so. And our algorithm is easy to formalize by using algorithmic work list, which is a unification of judgments and contexts. You will see it later. Also, we use continuation passing style for inference judgments. It's the first time to do so. Okay, now let's see the specification or the declarative system first by an example. We have a twice function here. Basically, it applies a function twice to the argument. It's a polymorphic function, right? And f here accepts the twice. So it accepts the polymorphic function, and it uses it in two different ways, int to int. So it applies to both a function int to int and bool to bool. So here the argument type, the argument t should be a polymorphic type. So if you apply f to twice, it's perfectly fine because the argument type matches the specification of twice. But if you want to apply it to identity, we'll expect it also works. But the compiler will ask, well, why does the type of identity function compatible with the expected argument type? And the short answer is the type of identity function is more general. And let's see very quickly how our declarative system got to this point. So we are using a bidirectional type checking. So basically, we have inference mode and checking mode. I believe you are familiar with that. And the task we are going to do is to infer the type of the function application f applied to identity. So what do we do here? We apply that rule. We first infer the type of the function, and then check if the argument matches the type, the argument type. All right, and we already know the type of the function, which is t. So we need to check identity function against the parameter type. And here is a subsumption rule. If you already know the thing you are checking, you first infer the type, right? The type of the identity function is for a to a, and then check if the subtyping hold. And we're back to the problem. So why this identity function is more general than the for b to b to b to b? Again, short answer is you just instantiate a with b to b, and they just match. Well, technically, we're using a predictive polymorphic subtyping set of rules. So let's see how it derives. The problem here is to compare the generality of two polymorphic types. So for the first step, we eliminate the for all on the right-hand side and introduce a fresh variable b to the context. Okay, this is for all right. And then we eliminate the one on the left. So it's for all left rule. And this rule is a little bit complicated. You need to come up with an instantiation, which is a monotype. Monotype are types that don't have false. And then open the left-hand side polymorphic function, polymorphic type with the monotype. All right, so the type we come up with is B to B. It must be well-formed under some condition. Okay, and after the opening, the structure basically match, and it works. As you can see here, the declarative subtyping rule needs us to guess a monotype, and yeah, it happens also for the typing system. For example, if you are inferring the type of a lambda function, you want to the declarative system just guesses the type. It's a function type, and also if you want to apply polymorphic functions to an argument, you must first instantiate. But we restrict the instantiation to be monotypes. All right. So that's why we need algorithm, because we cannot simply guess it from nowhere. So we need to find solutions with the help of meta variables. And first, I want to show you how Dunfield's algorithm works. They proposed the algorithm in 2013. The main idea is to solve meta variables on the fly, and they use a kind of non-standard judgment form, where there is an input context, a judgment, and also an output context. Okay, let's back to the example. So first, we do something similar to the for all right. We introduce a type variable to the context. And then we do something similar to the for all left. But this time we don't know the guess, so we insert the meta variable alpha. All right. And now the problem is to compare two functions. So we first compare their argument types in a reverse manner, and then the return type. So the first problem is easy. We just solve the unification variable to b arrow b. And the reason why we can solve that is because b is defined before alpha. So b arrow b is a valid solution for alpha. And that is also the input of the second branch. And at this time, we already know the solution of alpha. So why not just substitute it by context application? So basically use the context as substitution. We substitute the second branch, and it's become quite trivial now. So we just simply return the context because we don't solve anything more. Okay. And at this step, we don't just return the context, because if we return the context, there will be both b and alpha. But if you look at the input context, there are no alpha. Alpha is introduced because of the for all quantifier. So alpha should be garbage collected. Similar things happen here. B is garbage collected. And I don't show the details of the rules, but they use complicated methods like a marker there to mark the scoping and to collect garbage properly. Okay, a short summary. They use lazy substitution for information flow. So basically use the record alpha equals its solution to propagate the solution. And the type of algorithm we use is different from Hindley-Milner because the polymorphic subtyping is restrict on scoping. So we need to use output ordered context. It's a relatively easy to implement algorithm, but output contexts are very hard to formalize. And their garbage collection strategy is actually not perfect. We actually find a rule that can be improved so that it's more precise garbage collection. Okay, time to come to our algorithm. We use a work list. So what is a work list? First of all, we just focus on subtyping judgments. And the work list consists of type variable declarations, existential variable or meta variable declarations, or a judgment. So it's a mixture of variable declarations and judgments. Our main algorithmic relation is reduction. So we reduce from gamma to gamma prime, and we repeatedly do that until we reach the base case, which is the empty list. Okay, let's back to the example. We now have only one judgment in the context and no variable declared. Okay, and the first steps are similar to Dunfield's algorithm. We first introduce the type variable B to the context, and then we introduce meta variable alpha to the context. And then interesting things happen because we are splitting the context, splitting the judgment into two, right? So we have two judgments here and also two variable declarations. So they all exist in a single work list. And I want to emphasize is that both of the judgment share the context. So every variable in our work list is in scope, is declared. Okay, and we again focus on the first, the rightmost element of the work list. So we solve alpha to B2B. It's a valid solution. And then something even more interesting happens. Since we know the solution of alpha, we can immediately propagate the solution to all the elements in the work list. We do not need to keep it in the output context. Yes. And after the substitution, there are no occurrences of alpha left in the work list, so we can safely remove the declaration away. So that's the two things we are doing, substitution and remove the declaration. Okay, and things becomes easier, so several steps. At this time, we have a B left in the context or in the work list, and what we are doing is to do a garbage collection. So our work list is also an ordered context, so you can always you can only refer to the variable after it is introduced. So whenever there is a variable declaration on the top of the work list, you just delete it and everything's fine. No variable is free. Okay. And that's all for subtyping. But for the typing part, something more difficult happens. So we support the typing system by introducing the checking judgment, the inference judgment, and the application inference judgment. But for inference judgments, we need to use a continuation parsing style where the A is a binder. And let's see an example. So this is the subsumption rule, right? So the declarative system subsumption rule. If you want to check, you can first infer the type, and then you use the output of the infer for subtyping judgment. And this is exactly what we do for algorithmic. So since the type, so you infer the type of the expression E, and you don't know the type yet, but you will operate on that type later. So it's a continuation parsing style. Okay, a concrete example here. Yes, it's another example. So if you want to check the identity function against unit to unit, which is a simple instantiation, the first step is to use the subsumption rule. So first check, and then do the subtyping. All right. But infer a lambda function is not easy, and we promise to give you the best monotype we can in a declarative system, right? So now here we just assume that the type of the lambda function is alpha to beta. So we assume the input type is alpha. We just check the body against beta. So the lambda function is now alpha to beta. Then we can continue the chain by replacing the placeholder to alpha to beta. Okay, and then we simply can solve this beta. We can unify beta with alpha, and it becomes alpha to alpha for the identity function. And these steps are just subtyping things. All right. Quick summary. We have only one relation for our algorithm, while Dunfield's algorithm have 6, and we use eager substitutions. They use lazy substitutions. And I would say that our garbage collection is better because we simply remove the elements. We don't need to use any auxiliary markers, something. But since the number of rules is quite similar, we actually behave similarly. Yes, and our algorithm is easy to formalize, and we need some way to relate the algorithmic system with the declarative system. And the difference is that algorithmic system have unknown variables, so the meta variables. So we need to find a proper instantiation. So here are 2 examples. If you instantiate alpha with b, it seems valid for the declarative system. But if you instantiate it with unit, the declarative system will reject it. And that's the way we state the main theorems. So soundness, our algorithm always find valid instantiations. Completeness, if there are instantiations, we can always find one. And our algorithm is decidable. Okay, we formally verified all main theorems in the Abela proof assistant. And because Abela supports higher order abstract syntax, it's very easy to encode substitutions, which we use a lot in our algorithm. All right, in 8,000 lines. Quick summary, we are the first to formalize a higher ranked type inference algorithm. We propose a new way to solve the type inference problem by using work list. We can substitute eagerly. We use continuation parsing style inference judgments. Okay, and here are some related work. We previously used single context work list algorithm, but it does not work. The garbage collection is worse and no inference judgment support. There are also other works that uses lists of judgments, but they use one context per judgment, which means more contexts, and we take a different approach. Also, there are impredictive systems, which is undecidable in nature, so you need to navigate trade-offs, yes, for a decidable algorithm. Okay, last slide. Yes, you are encouraged to formalize important algorithms, and if you find difficulty on type inference algorithms, you can try our approach. Okay, thank you very much.
Thank you very much. I will start with a question from Slido. Is this a predicative or impredicative type system? In other words, can a type variable be instantiated with an arbitrary type?
Yes, our system is a predictive system. We only instantiate 2 monotypes, so we share the same declarative system as Dunfield and Krishnaswamy's. Yes.
Questions from the audience? Okay, then I'll ask. Oh, sorry. Yes, please.
So I think you presented an implementation, then you presented the formalization. How close are they linked? I mean, Abela formalizes over lambda prolog, so do you directly somehow magically run lambda prolog, or there's a separate implementation? And how do you closely argue that they are really like linked or something like that?
I'm not quite sure I got the
So you have an algorithm, so
Yes.
you may have tested with some kind of implementation
Mhm.
as a program, and then you have a formalization.
Oh, yes,
which-
we separately implement it and formalize it. We don't use something Bella provide, so we don't execute that. Basically, because we have a non-standard form, and it's very hard to execute in an environment that's given. Okay.
So another question from Silo, from Gerdo Erdi. Does your algorithm ever require annotations for types that are no more than rank 2?
So does our algorithm accept annotations?
Does your
maybe it's a yes. So we accept annotations that where you can write arbitrarily many for alls in it.
Okay. Questions from the audience? Yes, please.
So my question was more that if I have something that doesn't use rank 3 types or so on, if it's only rank 2 types, can your algorithm infer a type for it without me giving any type annotations?
Short answer is no. So it only works for higher order. It's meant to work for higher order, and it's predictive. So if you want the algorithm to guess, then it only guess monotypes. But if that works for your system, it is fine. Otherwise, if you are expecting it to infer something like for all A to A, it does not work.
So, and a last question from Slido as our next speaker sets up. Richard Eisenberg asks, why use your CPS encoding instead of just introducing a new unification variable?
The CPS style is, I understand what the question wants to ask. So the CPS style introduces a binder, right? And why don't use another sort of unification variable? The CPS style is actually a different structure, so it handles output properly. Otherwise, it's quite technical. So you must use CPS style, otherwise outputs cannot be properly stated, even if you use another sort of unification variable. And you can ask me if you are still have question on that.
Thank you very much. Let's thank our speaker once again.